Hello, I'm Elizabeth. As mentioned, I'm a Principal Software Engineering Manager at Microsoft. And I'm really excited to talk about what's currently a very hot topic in research, as well as in product areas, such as AI assistance, and that is Copilot, generative AI, and large language models. So I'm, like I said, a Principal Software Engineering Manager at Microsoft. And I've always had a passion for AI, data science, data analysis. I remember when I was watching 2001: A Space Odyssey and reading the book as a kid, there was a great AI in that movie named Hal, and he ended up sabotaging the entire spaceship, attacking the members of the crew. And I always wondered, is this a software glitch? Is this a hardware glitch? Is this, just what is this the optimal thing to do? Is to take over and get rid of the humans? Or has he just started competing with the humans? And has he become a superpower, AI power? So I've always been fascinated about that. I hold a bachelor's in computer science from Carnegie Mellon, as well as a bachelor's in policy and management from Carnegie Mellon. And then I also have a master's in computer science with a specialization in AI from Stanford University. I worked under Professor Andrew Ng, and I worked on the Stanford AI robot project as my primary research area. Previously, I've worked at a lot of large companies, small companies, startups, and I've been a software engineer, a data scientist, and an engineering manager. So today I'll talk about generative versus discriminative AI. Basically, how did we get to transformers and GPT as well? And then I'll talk about the actual applications, so the products such as Copilot, the AI assistants. And then I'll talk about specifically an area I work on, which is reasoning search and natural language understanding. And then we'll get into Q&A. So generative versus discriminative AI. Basically, you should use the right tool for the job, right? So in some cases, you may need generative models. And the idea here is that generative models, as we know, model the distribution of individual classes. So if we have some observable X and we have an outcome Y, we can model the joint probability distribution. And we can do that, and that's very valuable for, say, labeling data points, as well as determining the probability that we have a given X is a given value, and Y is another value concurrently. So for that, we actually have Bayes' theorem. And then Bayes' theorem has some assumptions which we find pretty valuable. So we model with Bayes' theorem assuming independence between classes A and B. And that's not necessarily true, as we learned from the talk earlier this morning. Sometimes there are relationships, but if we believe that there's independence between the variables, we can then assume that the probability of A and B is equal to the probability of A times the probability of B given A, and vice versa. And from there, we can model these joint distributions by using directed graphs. So we can go ahead and determine, hey, given A, with this probability, we can model A and B, and then with this probability of B, we can model A, B, and C, and we can chain events. For example, we could have a robotic agent going through the given states and looking for an optimal outcome. And so these directed graphs can be pretty valuable. We also have Markov chains, and the difference there is they're undirected graphs. So instead of directed, we can model going backwards and forwards, just how do these variables A, B, and C have a relationship? And then a very common example is, of course, the hidden Markov models. So if you know the probability, hey, in Boston, it's going to be sunny 40% of the time. It's going to be cloudy 30% of the time. It's going to be snowy or rainy, let's say 40% of the time. You also know the probability. If folks are eating ice cream, the weather is most probable sunny with a certain probability and so forth. Then even if you don't know the weather, you can go ahead and figure out this hidden variable of the weather given that. So again, that's a very good class of models that's used for predicting joint probabilities. For generating new data points in a probability distribution. And then we also have discriminative models. So those are very good for predictive power. So given you have an input X, what is the probability that you have a given outcome Y? And there's very classic cases of that. We have linear regressions. So in a city, let's say you know what homes have sold for of given square footages. And you can go ahead and model that by creating a line, a linear line with the best fit between all the houses, given X as the square footage and Y as the price. And then you can predict the price in a given area. Logistic regression, we all know, modeling, performing the logit. So we go between values 0 and 1. And then we have decision trees. Those are very good in game theory. So you have basically your sequence of steps, and you make decisions along the way. And then we have support vector machines. And so you can think of that as basically classification. And then with a linear SVM, you could have multi-dimensional classification as well. You could think of like 3-dimensional classification as a bunch of boxes that are set up, and they're basically performing barriers between the different classes. And then you can model all these possible barriers between different classes. So again, it depends on what you're trying to do the job. If you're trying to generate new data points, say question answering, generative models are a good way to go. If you're simply trying to predict based on a linear or quadratic function, you can use discriminative models. Okay, so now we'll talk about the evolution of transformers to GPT. So we can go back even to the 1980s. Many of us were not alive then. I was alive, but I was very young. So back then, neural nets became a very popular topic, right? How do we model the human brain and the neural connections? And the idea there is that can really tell us how to achieve AI. We can have, for example, something like in Westworld, we can replicate our own brains and put them in a robot, and we can live forever. So the start of that was actually in the 80s. But the problem is in the 80s, we had very limited computational power. And additionally, we didn't have the data sets we have. And so there was some great research, but it kind of fizzled out. And then we went into the other traditional models I mentioned. SVMs were really great for multidimensional space and so forth. But then what happened is in the early 2000s, we ended up having large-scale data from what? The internet, from computational models, from having more compute within the data center. And then from there, we were able to create feed-forward networks and RNNs. So feed-forward networks essentially are neural nets where each input maps to an output. And you can have hidden states. So you have all the inputs, and they are essentially neurons, your inputs coming in, and then you can connect to linear and nonlinear layers in between, step by step, to do processing over multiple data points using different weights. And then you have your outputs. Then from there, we went to RNNs, or recurrent neural nets. And let's say a good example of that is predicting the next word in a sentence. So if I'm sending a message, I don't remember, I get a suggestion. This is the next word in the sentence, right? So for recurrent neural nets, you're taking all the inputs, 1 through n minus 1, and you're predicting value n. And that's a beautiful thing. It really helps you. But when you're using something like gradient descent and you're taking the derivative with respect to the weights, you have a lot of weights. You have 1, 2, 3, all the way through n minus 1. And that means you can either hit the vanishing gradient problem or exploding gradient. And so if your gradient vanishes entirely, guess what? You're not taking steps. You're not moving towards the local minimum or maximum. And if your gradient explodes, you could be taking huge steps in the wrong direction to maximize. So then we got into LSTMs, and LSTMs are very useful to solve this problem. You can still use all the state up to value n to predict, but the difference is here, you can actually look at what the important factors are. So if I'm doing a presentation on LLMs and Copilot, let's say some of the important words there are LLM and Copilot, not the words the and a. So from there, we could give a higher probability at a given gate that we would forget those unimportant words like stop words. And then we would have a lesser probability that we would forget the more important words. And then also, with a high probability, we would probably want to remember, at least in the short term, more recent words. So we would want to remember values n-1, n-2 when we're predicting value n versus words earlier in the sequence. And then from there, we got into bidirectional LSTMs to not only predict forward, but forward and backward, which is really valuable. And then we got to this concept of attention. So similar to the gates, to forget to remember or to remember short-term, medium-term, long-term, we can actually assign weights to words. So how important is a given word or a representation in the sequence compared to others? And again, this is all good, but flow is sequential. So it takes a long time to process value 1 through value n-1, especially, let's say you're predicting an entire document or entire paragraph. So again, a classic case is translation, right? So I love learning English to Spanish, and you have to go step by step through the entire sequence. But with the paper, attention is all you need. Guess what? You can assign weights, and you can create an architecture, a neural net architecture, with the input, the output, and all the hidden layers that will process this data and do it all together in an inferencing stage, as opposed to you predict word 3 by going through words 1 and 2, you predict word 4 by going through 1, 2, and 3, and so on. Okay, and then the attention mechanism, you can think of it as query, key, and value. So the query could be the original English translation, the value could be the translation in another language, and the key, you could consider it the weights. And so when you take that, you could take the query transpose times the key, and then you get a score. You can take the softmax of that score in order to determine what the weights are, and then the weights would be the weight at any given element times the value at any given element. And some examples here. So query could also be like a question answering system. So for example, what color is the sun? And then the key could be the fact that you want to give higher importance to color and sun. The value could be yellow. And so you could apply this to all kinds of applications in order to determine what is the importance in the input and the output, and how can we relate them to each other through weights in a neural network. And so yes, we could use attention without the sequential flow. So another way of looking at it is, again, how important is the ith word compared to all the other words in the sentence, including itself? And you would have word embeddings through something like SBERT, Word2Vec, whatever it may be, that will give you the contextual relevance. But beyond that, you actually want to be able to compare to everything else for the given output you're trying to predict. Okay. So LLMs use a transformers architecture. And so this is based off of attention, like I said. It's a neural net. You have typically an encoder-decoder. A very classic case is the translation of languages, right? And then you can use the embeddings. You look at the position because we're doing everything at once. We're not doing everything sequentially. So in that way, we want to make sure that we represent the position. Is this the first word in the sequence, the second, the third? And it captures the long-term dependencies. And so walking through this really quick, so we have the encoder step, and what that'll do is take the input embedding, add the positional information, and then we will apply multi-head attention. Why multi-head attention? Because we're focused on different aspects. So for instance, if you're trying to predict the output translation, you could have one aspect of attention focusing on predicting the output word 1, one aspect focusing on output word 2, and 3, and so on. So you may have different things you want to focus on in your predictions. And that'll be captured through looking at different aspects of the input, for instance. Then we'll take that the output of the multi-head attention, and we'll sum it, and we'll normalize it. And then we'll put it through a feed-forward network. Like I mentioned before, feed-forward network is the input values. Every input has to be mapped to an output. Next, we have the decoder. So the decoder is, this is how we're looking at the output embedding and see how it maps to the input. So the output embedding, again, we take the positional embedding. We also do we do something a little different. We do mass multi-head attention. And we do this across the input and the output. Why? Because we're trying to relate the input and the output. But why are we masking? So let's look at translation. Let's say I'm translating, I love math, right? And I'm trying to predict the word math. I don't want to include math as part of my input embedding when I do the cross attention, because that's going to cheat. We want the model to learn to predict words. So when we're feeding the input to the output, we look at that. Also, if we're trying to predict, let's say, the second word in the sequence, love. So then we would mask the words love and math, because we want the model to be able to predict that. So when we're looking at different aspects, we apply different masking. Then from there, we add and normalize the output. Then just like the input layer, we do a multi-head attention. And then we apply a feed-forward network. Of course, at each step after attention, we add and normalize. And then at the output, we could do a linear layer and a softmax. Okay, and then just quickly running through this. This is, again, a very similar algorithm. You can see you take the key at each spot with the query transposed. And you can have different aspects of attention focused on different areas. When you take the softmax here, if you're looking at the overall attention, you take the softmax and also take into consideration the dimensionality of the key by dividing by the square root of it. And then, as described before, positional embeddings, you need to represent the positional information. Is this word 1, 2, 3, 5? And then when you do that, make sure you normalize. So you want to make sure that longer sequences aren't treated differently than smaller sequences. Okay, like I described before, with multi-head attention, you're focused on different aspects. For the translation task, you're focused on predicting the nth word, for example, for each aspect of attention. And then you can do the dimensionality reduction and concat the results and pass it through a linear feed-forward neural net layer. Okay, so how does this relate to GPT? That's a good question. Well, GPTs are transformers. You can see from the name, generative pre-trained transformers. And basically what we're doing is we're first modeling the data distribution in an unsupervised manner, right, on an unlabeled data set. And this is where we get into the responsible ethical AI side. Typically that's based on a large set of web-based data, might have some bias, but we're generating the data points from there. Then we do a fine-tuning task, which is actually labeled supervised learning, right? Where we then train it on something like, hey, ChatGPT, Q&A. So we want to train it to answer questions. And that's where the generative model shows that it's a great model for the task, because we're able to generate values together that are new, novel values. And that's how ChatGPT can output these new answers to questions. Okay, so that's great. That's the overview of transformers, even going way back to the 80s. But how does that relate today to Copilot and other AI agents? So right now the trend is we want to be able to use these GPTs to do tasks for us, to make our lives easier, more efficient. And they're AI agents or AI assistants who are assisting us. So one example of this is we can essentially take the user input or user utterance, and we want to do a task, like write a paper for us, or send an email for us, or find all our meetings and schedule a meeting. So we take that as input, we send it to the LLM for reasoning, and then we can apply search over the user's data, maybe their documents, emails, files, as well as the web data. And then from there, we'll use that as grounding. And then we can call an LLM again to synthesize the data, and then it can return to the user. And so that's how you can output that paper, the presentation. I won't say whether I use this to generate this presentation today or not. And then at the reasoning and search stages, language understanding is necessary. So that's an area that my team focuses on quite a lot. How do we understand the language that the user is telling us? So we basically understand the user's intention, and we classify their queries into domains, intents, and slots. So what we do is the intent may be, hey, I want to write a presentation for the conference I'm presenting at. Hey, I want to get all this data on generative AI. Teach me about transformers. And then that's the intent, is to learn something or create a presentation. Then from there, we need to understand entities. Okay, my presentation is for the Women in Data Science Conference. That's a very specific entity. My presentation needs to be on this topic. Topic is a type of entity. Or I'm trying to schedule a meeting with my friend. It needs to classify my friend. Who is that person? That's an entity. So again, there's different intent detections. We could have composition intent, search intent. You're just trying to learn. And there's structured entities in the user input, senders, receivers, time ranges, pertinent documents. So when you're looking at building your Copilot application or your application of LLMs, what are the stages you want to go through? So there's several stages. We have model selection. With LLMs, if we're using an LLM, a vanilla LLM out of box, we don't need to worry about model architecture because we just described the model architecture. It's a transformers-based architecture with unsupervised step and a fine-tuning step. So we just select the model we want. Then we do the hyperparameter optimization. How do we optimize the parameters for our task? Then from there, the common theme is prompt engineering. How do we prompt the LLM to get the output we want? From there, we can do something even more interesting. Instead of using a single prompt, we might want to select a prompt based on the task the user is doing, specifically the user input. And then beyond that, there's the idea that if you want a customized LLM, maybe you want an LLM just for astronomy. I've heard talks on astronomy today, or for network security. You could go ahead and add a fine-tuned layer or an additional layer on top of your LLM architecture, or create a completely new model using the same transformers-based architecture, but with your domain-specific data. So that's taking it a step further and fine-tuning or retraining the model in a domain-specific way. So how do you select your large language model? Well, now there's quite a few. I mean, this just came out. I can't believe this. How do I select? Look at all of these. But this is good. We have a lot of good choices. We have the CPU-based LLMs. So if I'm on a budget, I cannot afford an A100 GPU, this is what I need. Or I need something really fast. Like the user needs a response now. We don't want a chatbot where we just sit and wait and wait. Then maybe you want one of the smaller models. There's other considerations besides the cost of hardware as well as size of model. Another really interesting consideration is also what was the model trained to do? So some models are a mixture of expert models, and you may want multiple personas influencing the output of the model. Another thing, like Turbo GPT 3.5 is very good at generating programming languages. So it can code for you. So if you want a model that understands code, programming languages, that's a good one. So just like I mentioned before between generative versus discriminative AI, just like you want to use the right tool for the job, same thing here. You want to use the right LLM for you, and you might even consider your own small language model, again, maybe using a transformers architecture, but trained on your own specific custom data. Okay, so now that you've selected your model, you've determined the optimal hyperparameters for that said model, you want to do prompt engineering. There's all kinds of interesting techniques you can use in prompt engineering. You can send a single shot call to the LLM, one shot, few shot. You can use a chain of thought where you're reasoning over multiple states. You can ask the LLM for consistency. So you can say to the LLM, hey, what is the most probable output? Think about this query in multiple ways, and what is the most probable output in your opinion? And achieve self-consistency. Or you can call multiple LLMs and say, do you agree? What do you think is the correct output? That's another interesting thing. You can also, whenever you're doing it, you want to have context, instruction, input data, and outputs. You want to be very clear, just like you're teaching a child. That's a common theme in AI, start with a child model, right? You want to train it very specific, clear, understand the limitations, what is the model trained for, and then also give as much detail about the use case. And one thing we've observed is that smaller targeted models work quite a lot better, or smaller targeted prompts work quite a lot better. There's a paper called Lost in the Middle, where we find that the LLM loses the context in the middle, but is more likely to understand the beginning or the end of the prompt. So being very specific, that helps your LLM. And then how can you use it? You can generate art, you can do text classification, you can do question and answer, that's common, ChatGPT. You can use language translation, bug finding. You can help with grammar for your presentation. Again, not saying if I did that. Anyway, now once you've got your prompt, okay, what happens if it's just not doing a good job for you? You have so many different use cases. Your user is typing all these questions in different areas. And it's just not working for every single question. It doesn't work for health-related questions. So then you want to think, okay, beyond just a single prompt, what can I do? Another use case, we've actually run out of prompt space. There's no more tokens. We can't add more examples. What do you do? So one way is through dynamic prompts, and there's many ways of doing this, but you can essentially dynamically generate a prompt based on your user input. So I'm highlighting one way of doing this. We've had various success in different ways, but one way is you could have a bank of examples, and then you find the most similar example based on your use case, and then or the top N or top K similar examples, for instance. And then you use that in order to create a new dynamically generated prompt. And then you have very targeted examples, very similar to what the user is sending. And this can be valuable so that you can do it this way. Another way is you could just have a small subset of prompts. So you could, for different cases like emails or files or calendar, you could have a different prompt and you could detect the user's intent. Or web search, you have a different prompt. You have a different prompt for composition for a Word doc. Okay, then typically places like OpenAI recommend that you start with prompt engineering. You get as far as you can. But in some cases, that's not far enough. So you have fine tuning. And I consider this something like prompt engineering on steroids. So the idea here is basically now not just one prompt, but you have a whole set of prompts. And you can fine tune these prompts very specifically for your use case. So as part of your input data, you can send like the prompt, who the user is, and then the response. And then this is beneficial because instead of just struggling with prompt engineering, we actually go back to the world of training with data with LLMs, but we're augmenting the LLM. So we still have the same underlying model, which is awesome, but we're able to specifically train it for a very specific use case. And this is something that we're currently doing research in. So the jury is out, but we have seen much increased relevance from tuning our model for specific cases for the Copilot applications. And again, it reduces model variance. So we know sometimes LLMs can hallucinate, as we call it. They can get confused by the prompt instructions. This helps with this by reinforcing, like here's an example, even more than what you can do with only, say, 8K or 16K tokens in the prompt. And again, we've seen it improves metrics and saves effort. Sometimes wrangling with a prompt can be a little bit challenging. Okay, so what are some examples of products that use this? There's a lot of really cool products. PowerPoint, you can make a PowerPoint, you can talk in Teams, you can get answers to your questions, you can get a summary of your meeting transcripts, you can use it in Word to basically summarize content. You can look at all your data across your emails, your files, your messages. You can get really interesting results amongst all your work apps. Another one, which is interesting, is writing code for you, right? So raise your hand if you've used GitHub Copilot. Okay, about 40%, maybe 30%. So this will write code for you. So here's where we get into the ethical and responsible AI that we've been talking about. So is AI going to take our jobs? Like, I'm a software engineer, I'm a data scientist. Is it going to become the new software engineer? And this is actually a very serious question. So when we think about this, what we've seen so far is even though it's a very exciting new technology, it's really not able to take away from human edits. So it can make our lives easier, more efficient, we've seen that. But there's still the human needed. Now that said, there are companies that have gotten rid of customer support people on their team due to the fact that they can just use a chatbot for it. Recently, with the advent of this, people who work on data, report generation, even writing, we see that is a large issue in academia. But ultimately, that's been happening. But as we heard earlier in the conference, there's so many things the world needs. There's a lot of conflict in the world, a lot of humanitarian efforts needed. There's jobs such as teacher, nurse, that just simply aren't going away. Even now, we have GitHub Copilot, but we still need people to actually update the code, really apply it to a real use case. We need software engineers who are doing the prompt engineering, updating the code. So right now, we still see that the human interaction with this AI technology is really important. Just like the Industrial Revolution, it's a tool. We need to wisely use it, we need to govern it, but it can make our lives much easier. And so how do you do that? So as we talked about before, underrepresented populations. So we've heard of the stochastic parrots paper. We don't want just the data from the internet. That's not representative of every population, we know that. So we need to make use of a diversity of data from different groups, especially minority groups. We have human reinforcement-based learning, and that's really valuable to get human input, again, from different communities as much as we can. We need multiple people, and this is where I mean there's more jobs to be had to harness this technology. Looking at privacy, security threat models, I saw a very interesting poster presentation on that. How do we avoid these privacy and security threats? And we need different metrics. So everyone has bias. When I write a prompt, when I generate training data, I am biased. I have my own perspective. When I use the internet data to train a large language model, that data is extremely biased. So the more we can have more people included giving their data, providing their metrics, providing guardrails, the more we have open community source involvement, openness of discussion, that can really lead towards ethical and responsible AI. So that's about it about Copilot and LLMs. Thanks so much to the many colleagues who contributed here.